Hello, this is Jack Jackson. In this video, we're going to be talking about the product rule for derivatives. So what we have here is a GeoGebra app, and we're going to look at a couple of functions here. So we have a function f of x, which is the opposite of x to the 1/2. In other words, it's a square root function flipped over the x-axis. And we see a point a, f of a on there. And then we have a function g of x, which is good old g of x equals x squared. So here we have a couple of power functions. One of them's modified by a flip over the x-axis. And then we want to do the product of those two. So we want to multiply these two things together to get this. So whatever this y value is here times this one up here is the y value down here. And that's going to be true all the way across this particular one. Notice g is defined everywhere, but since f is only defined for positive numbers and 0, then the product is only defined for positive numbers and 0. So actually we might as well just be looking at the first quadrant there and fourth quadrant. All right, so the question is, what about the derivatives? Now we know that the derivative of a constant times a function is a constant times the derivative function. Okay. We know the derivative of a sum is the sum of the derivatives, and of course from that we can get the derivative of a difference is the difference of the derivatives. So a natural conjecture would be, hey, maybe the derivative of the product is just the product of the derivatives. Let's check it out. Let's see if that works. So I can click on this check mark here to see the tangent lines at this particular a. So at this particular a value, you can see the tangent lines to the function g here, the function f here, and the function p here. And of course, the slopes of those tangent lines are the vertical changes, these vertical vectors here, here, and here that you get when you go to the right one. And it's how much the graph of the tangent line goes up or down when you go to the right one. That's what the derivative is. So these are the derivatives you can see visually here. So the derivative of g is 3, and the derivative of f is negative 4.1, at least approximately, at that particular value of a, which at the moment is 1.5. Well, what happens if we multiply those two together? Do we get this down here? Let's see. Well, 3 times negative 0.41, I believe, is about negative 1.23. And yet, if you look here, the derivative of the product is not anywhere close to that, really. It's negative 4.59. So in fact, it doesn't work out. So here are the actual values that we're talking about. Here's the value of the points on the curve. So this is 1.5 comma negative 1.22 is that point. 1.5 comma 2.25 is that point. And 1.5 comma negative 2.76 is that point. Some of these may be rounded off. If the derivative, here we can see the derivative of g is 3. The derivative of f is negative 0.41. And the derivative of p is negative 4.59, as we see here. And once again, those do not multiply outright. So that's not the product. So, we may come back to this in just a minute. So there's some notes with this in there. Let's make this a bit bigger. And so if you look at these, since these are just power functions and their product is a power function, we can actually work out what the formulas are here pretty simply without knowing what a specific power rule product rule might be. So in this example, f of x is minus x to the 1/2. So its derivative, let's see, 1/2 times negative 1 is negative 1/2. Subtract 1 from the power, 1/2 minus 1 is negative 1/2. So its derivative is negative 1/2 x to the negative 1/2. So the derivative of g of x is x squared. So its derivative, of course, is just 2x. Well, what would happen if you multiply those two derivatives together? Well, if you multiply f prime and g prime, let's see, the 1/2 and the 2 cancels. We still get a negative 1 for a coefficient. And these, you multiply it two power functions there by keeping the same base and adding the exponents. So 1 plus a negative 1/2 is 1/2. In fact, that's the same as the original f of x. But it's not p of x. P of x is what happens when you multiply f of x and g of x together. Well, if you multiply these together, we get negative 1 times 1 is negative 1 for the coefficient. And we multiply these together by keeping the same base and adding exponents. 2 plus a half is 2.5, or 4 halves plus 1/2 is 5 halves. So p of x is negative x to the 5 halves. Now, since that's a power function, we know how to do its derivative. 5 halves times negative 1 is negative 5 halves for the coefficient. Subtract 1 from the power. 5 halves minus 1 is 5 halves minus 2 halves, which is 3 halves for the power. And of course, these two things are not the same. Of course, we knew they weren't going to be the same because these numbers didn't work out to be the same up in the example we were looking at. To give you some idea of what's happening and where the problem is, let's look at another example. Here's an example using some linear functions. So suppose this time, instead of using those functions we used above, suppose we say f of x is m sub f of x plus b sub f. So it's just a linear function. The m sub f, m sub g, b sub f, and b sub g are all constants. So similarly, g of x is m sub g of x plus b sub g. So this would be two linear functions. If we look at that, then the derivatives are just, the derivative of f is just m sub f, and the derivative of g is just m sub g. So these are constant functions. So these are pretty simple functions to look at. Well, what's going to happen is if we multiply those two derivatives, we're going to get m sub f times m sub g. But as you can probably guess, it's not going to be the same thing as the derivative of the product of the two functions. So the problem comes in right here. When we're multiplying these two functions to get p of x, we're not just multiplying these first terms or even just the coefficients like we are over here. What we're doing is we're having to use FOIL here, or the distributive property. So what do we get? Well, we get first times first is mf times mg, that would be x squared, plus, let's do last times last, bf times bg is the constant term. And to get the middle term, you do the f, the o and the I. The o is the outer product, so that's mf times bg times x, and the inner product is mg times bf. And we add those up like terms to get a middle term. Now we take the derivative. That's just a quadratic polynomial, so it's not too hard to do the derivative. Power 2 comes down front times this coefficient, so it's 2 mf mg x to the first power plus this coefficient here of the x is just by itself now, and the derivative of the last part is 0. And notice, of course, that is more complicated than just multiplying the two slopes. That's the two slopes are multiplied in there somewhere, but that's only part of what's going on. So this is a little bit more complicated setup. So what's really happening? How do we actually find it? Well, it turns out we can actually go through and do a derivation while we're doing the formal proof of it. So let's go through that here in just a second. Okay, so before we do that, let's set up a couple of things and remember this. Delta x is f of x plus h minus f of x. So f of x plus h is f of x plus delta f. Similarly, delta g is g of x plus h minus g of x. So g of x plus h is g of x plus delta g. We used a similar thing like this when we were working on, I think, the chain rule earlier. So in the numerator of the difference quotient, you're going to have f of x plus h times g of x plus h minus f of x times g of x. And so if we replace f of x plus h by this binomial, f of x plus delta f, and replace g of x plus h by this binomial, g of x plus delta g, and then of course we still have the f of x minus g of x, the product of these two blue ones is going to give us that FOIL idea again, that multiplying these out. So when you multiply these out, you actually get four parts, the f, the o, the I, and the l. And we can demonstrate graphically that FOIL, that distributive property, right here. Here's the f is this area, The O is the F delta G, that's here, and the G delta F is the I, and the L is the delta F delta G. You have a similar picture anytime you're visualizing the product of two binomials. You can illustrate it with four areas like this. And in fact, you can do exactly the same thing when you're multiplying two-digit numbers. You're going to have the same four areas. So this kind of gives you a visual of the FOIL part of what's going on here. But let's work out the algebraic proof. So once again, we're going to have this basic setup. And as we said before, our limit of, as h goes to 0, of our function evaluated at x plus h minus our function evaluated at x divided by h. Of course, our function evaluated at x is f of x times g of x, and similarly evaluated at h is f of x plus h times g of x plus h. And as we said here, we're going to replace f of x plus h and g of x plus h as f of x plus delta x and g of x plus delta g. Now we can do our little FOIL thing here. First times first, f of x times g of x here. The outer is f of x times delta g. There we go. The inner is g of x times delta f. And the last times last is delta f times delta g. And if you look, this first part cancels with the last part at the end, cancels with the first part here. All right, now I'm going to distribute the h into each part of these. So each of these is over h and make 3 fractions out of it, and then 3 limits. Okay, so we use one of our limit laws. So provided these 3 limits exist, that's going to work out. The f of x doesn't have anything to do with h, so it can be brought out front of the limit sign. Similarly, the g of x can be brought out front. And I want to think of this as the product of 2 limits. Leave the delta f over h here and the delta g here. But wait a minute. This right here is another way of saying g prime. This is another way of saying f prime, and there's another f prime. But that limit is 0. 0 times f prime is just 0. So that last term goes away. And that's basically saying that this little box here is going to really have no bearing on our derivative of our product. The amount that the product is growing is this amount plus this amount. So as this rectangle is growing, it's growing on this side and this side. It's growing on 2 sides, with this little corner not really turning out to matter too much. Okay, so that is deriving and illustrating the product rule, and we'll put it into work in our next video in evaluating some formulas.